Okay, so these are dates for upcoming events. And on the lectures page, the practice test, and as of a few minutes ago, the solution to it has been written up and posted. When we come back from break, so on Monday and Wednesday, the 24th and 26th, so around this time, I'll cover the last section of the chapter, 14.7, that's on general changes of variable instead of just the specific ones that we've been talking about. So the very last problem on the practice test is about that. So once you've seen this material, hopefully you can do that problem too. Okay. There's one aspect of the last example I did on Monday that I want to focus on a little bit more because I was kind of rushing it last time. Where you have a situation like this where you're trying to come up with limits in spherical coordinates, and the same thing can come up in polar cylindrical coordinates, where you have some sort of boundary like this, where you have some line of some slope, y is equal to mx. So in the example from last time, it was just y equals x. So you want this region, you want to use this to help specify your limits in theta. So in this case, this example drawn here, clearly theta equals 0 would be the lower limit. But what about this upper limit here? So for this one, if you keep in mind, this is your slope. If I have 1 unit of run and m units of rise, so rise over run for slope, and this is your angle that you're looking for, that you're trying to figure out for getting your limits for with respect to theta. By right triangle trig, we have tangent theta is equal to opposite over adjacent. So your upper limits for your integration is theta will be equal to inverse tangent of your slope. So if you're trying to integrate over a region using polar, cylindrical, spherical coordinates, in all of these cases you're using a variable theta, you can use that to get your limits. So in the example we had theta is inverse tangent of 1, which is pi over 4. So that's why we use pi over 4 as a limit in that case. If you have a somewhat more interesting region where it's bounded by 2 lines, like you can usually get an example like y equals x and y equals minus x. You could do the same thing for both boundaries. So in this case, you would get theta equals pi over 4, and then using the same arctangent, theta is equal to minus pi over 4. So that's how you can figure out limits for cases like that. So sometimes you need to go back and forth between what is the slope of a line and what is the angle corresponding to it, and that's how they're related. And yet another example of how this lower level math, like what you see in trig, just never really goes away. There's still a need for it, unfortunately. Okay. All right. Now, so now I want to spend a little time talking about applications for triple integrals, because we have one for double integrals. Because this is a single integral is area under a curve, a double integral is volume under a surface, but what about 3D? And actually, these applications for triple integrals also can be applied in the for double integrals too. seen the formula at one time or another. So mass of an object is equal to its density, which is often referred to using the Greek letter rho. So it's not a lowercase p. This is a lowercase p, something like that. So when it's curved like that, it's a rho. But I don't think I'll need to use both p and rho today, so there shouldn't be any confusion. And then v, of course, is volume. So if you have a simple shape for which you can compute volume easily, like a box, and the density is constant, that's no problem. You can just multiply them together. What if you have a more complicated shape? Or what if you have a density that varies? Like, for instance, certain rock formations, you can have a variable density throughout it. So you can use this within a double or a triple integral. So if you're doing the mass of a thin plate, also known as lamina, and the density is some given function, rho of xy. So that density would also account for whatever thickness that the plate would have, however small that may be. And if I use d to refer to, so my generic blob here, so this would be this thin plate that has whatever shape, then the mass is given by, I'll use little m to refer to the mass. It's just a double integral over d of the density. Okay, so just as mass is density times volume, the integral of density over a region is going to give you the mass. Because what's happening is you can think of this as multiplying a density by little bits of area. So this is playing a role of volume for a two-dimensional shape. And if you have a three-dimensional solid with density as a function of x, y, and z, and I'll use the letter E to refer to the solid, so whatever shape that might be. So m in that case is just going to be a triple integral over that solid of your density function. Okay. So in general, integrals are used to generalize formulas that are products like this one. So mass times volume, width times height, or three dimensions, width times height times length, velocity times time for total distance. So whatever kind of formulas they have, if they have a form of product, you can use an integral to apply those formulas in cases where things are not constant, like when density is not constant, or in the case of velocity not being constant to measure distance, things like that. Okay, now that we have a way of computing mass of these thin plates in 2D or solids in 3D, we can also use double or triple integrals to compute center of gravity. Okay, so the idea is, by center of gravity, if you want like an informal definition of it, is equal to the value of a point in which the object, and this is why it's an informal definition, behaves as if its entire mass is concentrated at that particular point. So that's going to depend on what is the density throughout the object, for coordinates. It's what shape does it have? So for example, if you're talking about a one-dimensional or two-dimensional object, it's where the object can be balanced. Like if I take this thin plate, if I want to balance it like on the tip of a pencil, at what point would it have to be resting on the pencil in order to have a chance of balancing? As a seesaw with different masses at each end, at what point should it rest on to have balance? So we can use similar ideas. So we would actually use the mass to help us to compute the x, y, and z coordinates of the center of gravity. So, now, first I'll talk about a two-dimensional case, and then it'll generalize easily to three dimensions. Okay. So, the center of mass so it's a point in two-dimensional space, and I'll just name the coordinates x bar and y bar. So a formula for these are just mx over m and my over m. So m is the mass from before. Sorry, I have these backwards. Okay. So I have to have the opposite variables here. So my, so the notation is going to be kind of weird here. So D is my two-dimensional object, my thin plate. I'm integrating, before I had just a density to get the mass, but now I throw in x. Now, it seems kind of strange to have a subscript of y when I'm integrating x. It seems like a recipe for confusion, but it'll make more sense when I go to the 3D case. And the reason for that is if you're in the xy plane and you have some point, then what is x? X is the distance of your point from the y-axis. So this m sub y is called the moment of your object D around the y-axis. So that is why it has y as a subscript. It's just that we have to use the other variable x to give the distance from whatever we're taking the moment around. And then similarly, mx, moment around the x-axis, what we have here is the distance from the x-axis, which would be y. Now, so what we get is, so these come from formulas for the moment of a point mass around an axis, and we just do that for every single point in the entire object. So integrating them gives us these two moments for all of D. So then, what we're doing is, if I were to express this center of gravity, center of mass, okay, so center of gravity. Oh yeah, well, you can use either term for it. If I express it as integrals, so that's the x coordinate, and then okay. So if the density was constant, I could pull these densities out and it would cancel. And then down below, all you would have is the area of D. So in effect, it would be, this would amount to like the average x coordinate of all points in D. And this would be the average y coordinate. So you can think of these as being weighted averages of x and y, the x and y coordinates of all points within D. And the weighting is given by the density. So where the object is denser, those points will have more weight. So they'll more heavily influence the location of the center of mass. Okay. Now, for the 3D case, it's similar. So the center of mass, x bar, y bar, z bar, we have m y z over the mass, the x coordinates, m x z for the y coordinate, and m x y for the z coordinate. So notice the subscripts are, if I want the x coordinate, I have all the other variables. Here for y coordinate, I have everything but y. For z coordinate, I have everything but z. So for instance, the moment around the plane, well, so I could say it's, we're in 3D. And x times the density. This is a triple interval now. All right, so this is my definition for m, y, z. So here's my point somewhere in three-dimensional space, and what I want is, not that, the x coordinates is going to be the distance from x equals 0, which is the yz plane. So instead of in two-dimensional case, we have myz is a moment around the y-axis. This is a moment around the yz plane. So we're taking basically a weighted average of all of the x-coordinates of all points within your solid by dividing by m, which is the integral of just the density. So then I have similar definitions for a moment around the xz plane, where we integrate y, and then the xy plane, where we integrate z. Now, I do not have a problem like this on the second test, but I reserve a right to put one on the final. Saying, okay, here's a object, I describe a shape, so you know how to get your limits for D or E. What is the mass? What is the center of gravity? So these formulas would come up for that. Okay. Is there any questions about these? If you don't remember the terms, like moment around y-axis or moment around yz plane, as far as what to integrate, for x-coordinate, integrate x times density. For y-coordinate, it's y times the density, and so on. But you don't forget to divide by the mass, which is the integral of just the density. Now there's other moments. This is on page 92 to 93 in the notes. So for instance, these moments, we're integrating x, y, or z to the first power. Now, second moment is where you integrate something squared. And there's second moments, third moments, and so on. So one more moment I can describe. There's actually a second moment. So this is for rotation. So for the indication of a tendency to rotate around an axis. So for example, Ix would be the integral over a two-dimensional shape of y squared times the density. So this is tendency to rotate around the x-axis, which is why it's called I sub x. But what is the distance to the x-axis? That's y. So if it was just y to a first power, that would be for center of mass. But in squared, it gives a rotational tendency. Okay, and this is for a 2D case, and for a 3D case, we have Ix would actually be the integral over solid, not just y squared, but y squared plus z squared times the density. Okay, so because for that point, that would be, so we're using y and z to give distance to the plane x equals 0. Because the fact that we just zero out the x coordinate, then that would be the magnitude of the entire point. Okay. Right. So this is also, so both of these have that meaning. Tendency to rotate around the x-axis. Okay. So in 3D, so here's the x-axis right here. So whatever your point is, the shortest distance from this point to anywhere along this line, because the distance from this point to the origin is square root of x squared plus y squared plus z squared. But if you only want the distance not to this point, the origin, but to this axis, shortest distance is what keeps the x-coordinate the same. And then we're subtracting off the making y and z coordinates 0 to get to this axis. So this distance is a square root of y squared plus z squared. The distance to the x-axis. Sorry if I flubbed this up earlier the first time I mentioned it, but at least what I've written on the board is correct. Okay, so we could have similar things like I, y, and I, z to be tendency to rotate around the y-axis or z-axis in three-dimensional space. So whatever axis you're rotating around, you take the sum of squares of the other variables. So really that applies in both 2D and 3D. Okay. All right, so those are some application problems. Again, it's something that could come up on a final, since that's comprehensive. Okay. All right, so many people here today, but let's make sure also you did drag yourself in here right before break. Get credit. Okay. Now, does anyone have any homework questions of any kind? Okay. Actually, while you're doing that, I'll get up MyLabs Plus. Number 9? Mm-hmm. Okay. Well, the internet's cooperating better today, kind of. Not really saying much. Okay. So finding the average value over an annulus.
I didn't write.
Um,
Never mind, I didn't write.
Okay, average value of 1 over r squared. Do you have a problem written down anywhere?
I just wrote down.
Okay, well, please let me know if this rings a bell when I write it down.
I can bring it up.
Okay. Okay. So this is the average value of 1 over r squared over the annulus. Okay, so that's several points r and theta, such that 3, so r between 3 and 4. Does that look like? Does that ring a bell at least? Okay. All right. Okay.
Because I don't remember.
Okay. All right. So what we're looking at is sort of two concentric circles. So this is r equals 3, r equals 4. So in general, average value, so whatever function f over a two-dimensional region D would be equal to 1 over the area of D times the integral over D of your function f. Okay. Now, so in this case, we would have 1 over r squared, and then don't forget your extra factor, r d theta. Okay. And then you need to get the limits for this. And what would the limits be, like first for r and then theta?
R is 3 or 4.
Yeah. And what about theta? What angles are allowed? All of them, which means
0 to 2 pi.
yeah, 0 to 2 pi. Okay. Now, well, first we work that out. That would give you this part. If I need to divide by the area, now the area, of course, would be the integral of 1 over it, but you don't need to do that in this case because you can figure out the area of these circles using the appropriate formula pi r squared for each, and then subtracting them. Just because you want the area of this region between. So then you would just take this and then divide by that. So you see how to do it from there? Okay. Any others anyone wants to bring up? Okay. There's still plenty of time for the to be prepared for a test. We still have one more section to go. Okay, and actually, well, I don't have anything more, so I guess, well, my break starts now. And hopefully it starts for at least some of you now too. No, more classes?
Yeah.
Oh, okay. Well, I'm flying too. To San Francisco. Stanford, but I still work with people there.
That'll change the, and then the
Yes.